Game theory is a branch of mathematics that studies decision-making in situations where multiple individuals or groups are involved, and the outcome of each decision depends not only on the decision of the individual or group, but also on the decisions of the others involved. Game theory is used to analyze a wide range of situations, including economic interactions, political campaigns, and even evolutionary biology. At its core, game theory is concerned with the analysis of strategic interactions, where each player is aware of the actions of the others and acts accordingly. This means that game theory is concerned with the analysis of situations where the behavior of one player affects the behavior of the others, and vice versa. This is often represented using a game matrix, which shows the possible actions of each player and the corresponding outcomes of those actions. One of the most famous examples of game theory is the prisoner's dilemma. In this game, two prisoners are arrested and accused of committing a crime together. The prosecutor offers each prisoner a deal. If one prisoner confesses and the other remains silent, the one who confesses will be given a reduced sentence while the one who remains silent will receive a harsher sentence. If both prisoners confess, they will both receive a moderate sentence. If both remain silent, they will both receive a light sentence. The key to the prisoner's dilemma is that each prisoner's decision is based on what they believe the other prisoner will do. If one prisoner believes that the other will remain silent, then they will confess in order to receive a reduced sentence. However, if both prisoners confess, they will both receive a moderate sentence. This means that both prisoners have an incentive to confess, even though both would be better off if they both remained silent. The prisoner's dilemma illustrates a central concept in game theory, the notion of a dominant strategy. A dominant strategy is a strategy that is always the best choice for a player, regardless of the choices made by the other players. In the case of the prisoner's dilemma, confessing is a dominant strategy for both prisoners. Another key concept in game theory is Nash equilibrium. A Nash equilibrium is a situation in which each player's strategy is the best response to the strategies of the other players. In other words, no player has an incentive to deviate from their current strategy, given the strategies of the others. The prisoner's dilemma has a unique Nash equilibrium, in which both prisoners confess. Game theory can also be used to analyze more complex situations, such as auctions. In an auction, multiple bidders compete for a single item, and the winner is the bidder with the highest bid. The challenge in an auction is to determine the optimal bidding strategy, given the strategies of the other bidders. One common type of auction is the sealed bid auction, in which bidders submit their bids in secret, and the highest bidder wins. In a sealed bid auction, the optimal bidding strategy is to bid one's true value for the item. However, if other bidders are uncertain about the true value of the item, they may bid lower than their true value, in order to avoid overpaying. This means that the optimal bidding strategy may depend on the beliefs of the other bidders. Game theory can also be used to analyze voting systems. In a voting system, voters must choose between multiple candidates, and the candidate with the most votes wins. The challenge in a voting system is to determine the optimal voting strategy, given the preferences of the other voters. One common voting system is the plurality system, in which voters choose a single candidate, and the candidate with the most votes wins. However, the plurality system can lead to strategic voting, in which voters choose a candidate who is not their true preference, in order to prevent another candidate from winning. This means that the optimal voting strategy may depend. Another voting system is the ranked choice voting system, in which voters rank the candidates in order of preference. The candidate with the lowest number of votes is eliminated in each round, and the process continues until one candidate has a majority of the votes. Ranked choice voting can mitigate the problem of strategic voting, as voters can vote for their true preference without fear of wasting their vote. In addition to its applications in economics and political science, game theory has also been used to study evolutionary biology. Evolutionary game theory applies the principles of game theory to the study of the evolution of biological traits. This allows researchers to model how different traits may evolve over time, and how they may interact with other traits. For example, evolutionary game theory has been used to study the evolution of cooperation. In a classic example, researchers studied a population of birds called the pied flycatcher. These birds are known to exhibit a behavior called nest guarding, in which males guard their mate and their nest from other males. Researchers found that when the population was small, the males were more likely to guard their nests. However, when the population grew larger, the males were less likely to guard their nests, as the costs of guarding became higher. Evolutionary game theory can also be used to study the evolution of social norms. Social norms are unwritten rules that govern behavior in a society. These norms can be beneficial for the society as a whole, but may not be beneficial for individuals. For example, the norm of honesty may benefit society by promoting trust, but may not benefit individuals who are tempted to cheat. In conclusion, Game theory is a powerful tool for analyzing decision-making in a wide range of situations, from economic interactions to evolutionary biology. By modeling strategic interactions, game theory allows us to understand how different decisions may affect the outcomes of a given situation. Whether we are analyzing auctions, voting systems, or the behavior of animals, game theory can provide insights into the complex dynamics of decision-making.